Hi students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as gravitation. Let's start. First let's start with Newton's law of gravitation. Now, what does Newton's law of gravitation state? It states that every body or every particle of matter attracts any other particle with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance. I have, say, let's assume I have a body of mass m1 here. I have a body of mass m2 here. Let's assume that the distance between them is, say, r. R is the distance between them. Then I can say that this body m1 is going to exert a force of attraction on m2, and m2 will also exert a force of attraction on m1, right? So I can say that every particle, Newton's law says that every particle of matter attracts every other particle with a force, every other particle of matter with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance. That's my Newton's law of gravitation. Okay, so that means, as I've already shown you, that if m1 and m2 are the masses of two particles and r is the distance between them, then in that case I can say that the force of attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. To convert proportionality to equality, you multiply by g, where g is your constant of gravity, is your constant to convert proportionality to equality. G m1 m2 upon r square. Fine, do we get this thing here? Now, in which case I can say g is a constant, where g is a constant and is called as constant of gravitation. Is called constant of gravitation. Fine, do we get this thing here? Now, the SI units of G, I can say that G is equal to Fr square upon m1 m2. Therefore, I can say that the SI units of G will be nothing but Newton meter square per kg square. Newton is force, meter square is r square, and m1 m2 therefore kg square. Once I have this, then I can also find out the dimensions. The dimensions of G are going to be equal to, how do I get this? The dimensions of force, dimensions of radius square upon dimensions of m1 m2. Force is mass into acceleration. Acceleration is displacement upon time square. So mass into displacement upon time square. This is L raised to 2 and this is m raised to 2. Right? So your answer will be nothing but m raised to minus 1, T3 and L3 and T minus 2. Those are going to be your dimensions of G. Fine, do we get this in here? Now, experimentally, this value of G was found out, and that is called as the universal constant or the gravitation constant, and the value of G was found out as 6.673 into 10 raised to minus 11 Newton meter square per kg square. That's the experiment value of G. Assuming that the gravitation force between two bodies, right? So in that, and this was found out in 1798 by a scientist called as Henry Cavendish. Okay, so that's Newton's law of gravitation. Now let's find out the relationship between constant of gravity and acceleration due to gravity. Constant of gravity and acceleration due to gravity. Right? Now, let us consider a body of mass m situated on Earth. Consider a body of mass m situated on Earth. Right? Let's assume that capital M and R are the mass and the radius of the Earth. Mass and radius of Earth. Right? Once I know this, let's also consider that G is the acceleration due to gravity. G is acceleration due to gravity, right? In which case I can say that gravitational force by Newton's law, if I apply Newton's law of gravitation, I can say that by Newton's law of gravitation, I can say that F is equal to gmm upon r square. G is the universal constant of gravity. M and M are the mass of the Earth and the mass of the object. R is the distance between the center of the Earth and the object. Right? Now, we know that, guys, the weight of the body on Earth is equal to the gravitational force exerted on the body right? In that case, I can therefore say that mg, weight of the body, should be equal to gravitational force, that is gmm upon r square. That means I can therefore say that m and m gets cancelled, therefore g is equal to gm upon r square. So gravitational acceleration is nothing but gm upon r square. Now here the body was situated on the surface of the earth, where r, this is when the body is situated on surface of earth. Now if the body is not situated on surface of earth, if it is at height h, in case the body is at height h above the surface of the earth, if the body is at height h above the surface of the earth, in that case I can say that weight of the body should still be equal to the gravitational force. Weight of the body is mg, gravitational force is gmm. The only difference is my distance will be r plus h the whole square, right? So in that case I can say we'll call this gravitation as gravitation at height h. So m and m gets cancelled, so I can say gravitation at height h is gm upon r plus h the whole square. Finally, we get this thing clear? Now, next thing, what do we mean by a satellite? What do we understand by a satellite? A satellite is nothing but it is a man-made body revolving round the earth under its gravitational influence. Man-made body revolving round the earth, revolving round the earth under its gravitational influence. Influence. Right? Do we get this thing here? Now, let's see this. Why do we need a two-stage rocket to launch a satellite? Why is a two-stage rocket required to launch a satellite? Let's see this. This is my first stage, second stage, satellite. Why do I require a multi-stage or I need a two-stage rocket to launch a satellite? One, if this is the satellite situated on the surface of the earth, there are two things that have to happen to the satellite. One, necessary force has to be provided so that the satellite escapes the gravitational field of the earth. So the first thing that is to be done is I need to provide it with the necessary force so that it just escapes the gravitational field of the earth. Right? Once it has escaped the gravitational field of the earth, the first stage is detached. During that process, the satellite is turned by an angle of 90 degrees. The satellite is turned by an angle of 90 degrees. And then the second stage provides it with the necessary velocity so that it keeps revolving around the earth. That is the reason why you need a multi-stage rocket to launch a satellite. The first stage of the rocket will push the rocket beyond the gravitation field of the earth. The second stage will provide it with the necessary velocity so that it revolves around the earth. Fine, do we get this thing here? Now, so the velocity that is required to escape the gravitational field of the earth is called as the escape velocity. What is escape velocity? It is the minimum velocity that has to be given. It is the minimum velocity that has to be given to the satellite so that it escapes the gravitational field of the earth. Right? It is the minimum velocity that has to be given to the satellite so that it escapes the gravitational field of the earth. Right? Then, besides that, I want the satellite to revolve in circular orbit around the earth. Hence, it has to be provided with a necessary velocity. This velocity that it has to be provided with is called as critical velocity. Right? So, what is critical velocity? Critical velocity is the horizontal velocity of projection for which the satellite will revolve in a circular orbit round the earth. Right? What is critical velocity? We'll just write this down, people. Escape velocity. It is the minimum velocity that should be provided so that the body escapes the gravitational field of the earth. Right? So the first stage of the rocket will provide the rocket with the necessary escape velocity. The second stage of the rocket will give the satellite its critical velocity. What is critical velocity? Critical velocity is the horizontal velocity. Critical velocity is the horizontal velocity of projection. Critical velocity is the horizontal velocity of projection for which a satellite revolves in a circular orbit, in a circular orbit, right? Revolves in a circular orbit round the Earth. The Earth. Fine, that is what is called as its critical velocity. Now let us see what happens if my critical velocity is not accurate. Let's consider four cases that may arise depending upon the critical velocity of projection. Different cases of critical velocity. First case, let's assume that if the critical velocity, if the horizontal velocity, if horizontal velocity provided to the satellite is less than the critical velocity. You have Earth, this is your satellite which is supposed to revolve at this orbit, right? Now it has to be provided with the necessary horizontal velocity so that it keeps revolving in that orbit. But instead of that, suppose if it is not provided with the right kind of horizontal velocity, in that case what will happen is that the satellite will move in a parabolic path and will come and fall on the surface of the Earth. So if the horizontal velocity is less than the critical velocity, then the satellite moves in a parabolic path and falls on the Earth. Right? Next, let's see another case. Suppose if the horizontal velocity is just equal to critical velocity. Second case, if horizontal velocity is equal to critical velocity. If the horizontal velocity is equal to the critical velocity, then in that case the satellite will keep revolving in a circular orbit around the Earth. The satellite will revolve in circular orbit around the Earth. Right? Next, if the horizontal velocity is greater than the critical velocity, if horizontal velocity is slightly greater than the critical velocity, right? If the horizontal velocity is slightly greater than the critical velocity, in that case the satellite will move in elliptical orbit around the Earth. Right? Next, D. If the horizontal velocity is far greater than the critical velocity, right? If the horizontal velocity is greater than the critical velocity, then the satellite would break the gravitational field of the Earth and escape into the space, right? The satellite would break the gravitational field of the Earth and escape into space, right? So this is what are the different cases that will occur. Now that means from this discussion it is very clear that you have to make sure that the critical velocity is correct. Only then the satellite will revolve around the earth, right? Let us try to derive an expression for critical velocity. Let's try to derive an expression for critical velocity. Let us assume that Earth, center of the Earth, radius of the Earth is r, right? Let us assume that you have a satellite moving at a height h above the surface of the Earth. This is the height at which the satellite is moving above the surface of the Earth. That means the total distance between the center of the Earth and the orbit of the satellite is r. Let us assume that it has been given the necessary horizontal velocity Vc. Vc is the necessary horizontal critical velocity, right? So let us consider a satellite of mass m. Consider a satellite of mass m raised to a height of h above the surface of the earth, above the surface of the earth, right? Now let us consider that it is projected with a horizontal velocity of Vc. Consider that it is projected. Consider that it is projected with horizontal velocity of say Vc, right? Now I can say that if the satellite is going to revolve in the circular orbit, then the centripetal force acting on the satellite is going to be mvc square by r. That is going to be the centripetal force that is going to act on the satellite. And what is going to provide that centripetal force? That centripetal force is going to be provided by the gravitational force between the satellite and the earth, right? Which is going to be provided by the gravitational force between earth and satellite, right? In which case I can therefore say that gravitational force is equal to the centripetal force, right? Now gravitational force can be given by Newton's law of gravity, which is nothing but gmm upon r square, right? Centripetal force is we know as mvc square by r. So r and square gets cancelled, m and m gets cancelled. Therefore, I will get vc square is gm upon r. Therefore, I can say that vc is square root of gm upon r. But r is nothing but r plus h. Therefore, I can say that vc is square root of gm upon r plus h, right? So the critical velocity is going to be equal to gm upon r plus h. But we know that gravitation at height h, we've done this derivation, guys. that gravitation at height h is gm upon r plus h the whole square, right? So in that case I can say that gm is nothing but gh into r plus h the whole square. If I substitute this in the equation of Vc, I'll get therefore Vc is square root of gh into r plus h the whole square upon r plus h. R plus h and r plus h gets cancelled, so square root of gh into r plus h. That's another expression for Vc. Vc is nothing but gravitation at height h multiplied by the distance. Fine, did you get this in here? Now, if the satellite is revolving close to the surface of the earth, if the satellite is revolving close to the surface of the earth, if it is revolving close to the surface of the earth, that means h is going to be very, very small as compared to r. That means in that case r plus h will approximately be equal to r, right? Where therefore my centripetal force will be nothing but mvc square by r, and my gravitational force is going to be nothing but gmm upon r square. Therefore, I can say that since centripetal force is provided by the necessary gravitational force, I can say that mvc square by r is nothing but gmm upon r. M and m gets cancelled, therefore you will get Vc square is r square, right? So therefore I can say Vc square is gm this is the centripetal force is going to be mvc square by r, gravitational force is going to be gmm upon r square, right? So in that case r and square gets cancelled, so you will get Vc square is gm upon r. Therefore I can say Vc is square root of gm upon r, right? Now I can also say g is, we have found out the value of g to be gm upon r square. Therefore I can say that gm is equal to gr square. Substitute this value in Vc. Therefore I get Vc is square root of gr square upon r. Therefore Vc is equal to square root of gr. Right? That is my expression for critical velocity. Now let's derive an expression for periodic time. Now first of all, what do we understand by periodic time? It is the time taken by the satellite to complete one revolution round the earth. It is the time taken by the satellite to complete one revolution round the earth. Right? So in which case I can say that now when the satellite is moving round the earth, it is moving with a critical velocity, right? So I can say that the critical velocity should be equal to the distance covered by the satellite. Now in one revolution, the distance covered by the satellite is the circumference of the orbit. Orbit divided by time. Velocity is distance upon time. Therefore I can say Vc, the circumference of the orbit is nothing but 2 pi r upon t, assuming that the satellite is at a distance of h above from the surface of the earth. But we have already derived that Vc is square root of gm upon r. Therefore I can say that square root of gm upon r is nothing but 2 pi r upon t squaring. If I square both the sides, I will get gm upon r is 4 pi square r square upon t square, right? In which case you will therefore get that t square is 4 pi square r cube upon gm. Cross multiplying, t square goes up, gm comes down, r goes up to give you r cube. So therefore I can say t square is equal to 4 pi square upon gm into r cube. But 4 pi g and m are constant, therefore I can say that t square is directly proportional to r cube. So for a given satellite, the square of the periodic time is directly proportional to the cube of the radius of the orbit. Fine, do we get this thing here? Now I can also say that we have already derived that t square is 4 pi square r cube upon gm. Take square root on both the sides. If I take square root on both the sides, this will be 2 pi square root of r cube upon gm, right? Now this can be written as t is equal to 2 pi root of r cube. R is nothing but r plus h the whole cube upon gm. So time period is going to be 2 pi root of r plus h the whole cube upon gm. But gh is nothing but gm upon r plus h the whole square. Therefore I can say that gm is gh into r plus h the whole square. Substitute this value of gm. In that case you will get, therefore t is equal to 2 pi root of r plus h the whole cube upon gh into r plus h the whole square. So in that case t will be 2 pi root of r plus h upon gh. That is another formula for time period. Fine, do we get this in clear? Okay, we will stop this here for the day. Thank you very much.